Hello, this is chapter 11, which is reactions of alkyl halides. And reactions are nucleophilic substitutions and elimination reactions. These both are actually one of the most widely occurring and versatile reaction types in organic chemistry because we can use simple alkyl halides to convert them into very useful organic compounds like alcohols or other halogen containing compounds or cyanides or nitriles, etc. In the previous chapter, we had discussed the different types of alkyl halides. I'm just going to review that quickly here. So you should be able to identify a primary alkyl halide. For example, this one would be a primary alkyl halide because the halogen is connected to a primary carbon atom. A secondary alkyl halide where the halogen is attached to a secondary carbon atom. A tertiary alkyl halide where the halogen is attached to a tertiary carbon atom. And in addition, we also looked at what are called as allylic halides, which are halogens attached to the allylic carbon atom, which is the carbon next to the double bond. And we have benzylic halides, which are halogens which are attached to the benzylic carbon atom. This is the benzylic carbon atom. And then we also have the aryl, where the halogen is attached to directly to the benzene ring. And finally, the vinyl, where we have the halogen attached directly to the carbon atom on a double bond. Okay, so this is primary, secondary, tertiary. This is allyl. This is benzyl. And we have the aryl and vinyl. Okay. So we'll look at different reactions of these compounds, and actually you will also be doing a lab that is associated with this reactivity of alkyl halides. So some of the topics that we'll be discussing in this chapter are given here. So we'll start by comparing substitution and elimination reactions. So the fact that the carbon-halogen bond is polar in nature makes this carbon atom here very electron poor, and therefore they can either undergo substitution reactions or elimination reactions. Okay, so sometimes the same reagent, so for example the OH minus here is actually bringing into the both reactions. So this is acting here as a nucleophile and replacing the Br with the nucleophile. So it's a nucleophilic substitution reaction. We're substituting a halogen with a nucleophile. And here what is happening is we are eliminating the halogen out of this. Also we are eliminating the hydrogen out of this. So this is an elimination reaction. So we're eliminating an HX or a HBr molecule to keep the alkene. Now, substitution reactions were discovered in 1896 by the German chemist Paul Wanden, and it was seen that in a nucleophilic substitution reaction, if you take the halogen, which is generally, we refer to it as a substrate. So if you have a substrate which has got a good leaving group, that's important. For a substitution reaction to happen, we should have a good leaving group which can be substituted with a nucleophile. Okay? The nucleophiles can either be fully negatively charged, or they can also be neutral species, like a water molecule can act as a nucleophile, or it can act as a nucleophile, right? And then the resultant product would be where the halogen has been substituted by the new incoming nucleophile and the leaving group is removed from the substrate. It was seen that whenever some of these reactions involve an inversion of stereochemistry. Okay, so that means if you have a chiral center, then the reaction with a strong nucleophile like this would result in an inversion of stereochemistry. So for example here, whatever the stereochemistry was, that is reversed in the product here. Okay, so here we have the tosylate. This is a good leaving group. Okay, this is not a halogen, but it's similar to a or actually one of the best leaving groups, which is called as tosylate, and it is coming out of the plane here. But here the new nucleophile, which is your acetate ion here, this is your acetate, it replaces the tosylate by also by inversion of configuration. So for example, if I take this question here, you are given a organic compound which is 1-bromo-1-phenylethane, and then we are reacting it with Na plus Cn minus here. Cn minus is my nucleophile. Na is there only to maintain the neutrality. So if we look at this, is actually a chiral center. So if we write this in an three-dimensional structure, so if we had this one, this Br coming going to the back and hydrogen coming out at this chiral center, if you react it with cyanide, then the product where the Br is replaced by the cyanide, but then also inversion of stereochemistry has taken place. So we started with an R compound, and now we end up with a S product. Okay? So let's look into details of the kinds of substitution reactions. So in every chemical reaction, there is always a direct relationship between the rate at which the reaction occurs and the concentration of the reactants. So when we measure this relationship, we measure what is called as the kinetics of the reaction. So for example, if you take a look at this reaction, we have an alkyl halide, which is CH3Br, and we are reacting it with a nucleophile, which is OH minus, and to get the product where the Br has been replaced by the OH, and then the Br is given out. Okay? So it has been seen that at a given temperature, and if we keep the solvent and the at a given solvent and a concentration of the reactants is given to us, the substitution always occurs at a certain rate. Okay? And it is seen that if we double the concentration of this OH minus, the concentration of the rate of the reaction also doubles. Okay. Similarly, if you double the concentration of this substrate, okay, so this is my nucleophile and this is my substrate, and if you double the concentration of the substrate, then also the rate of the reaction is doubled, which tells us that this particular reaction that we have here is a second order, it follows a second order kinetics. Okay, that means the rate is dependent upon the substrate. Okay, so the rate is dependent upon the substrate, or we can say proportional to the substrate and also to the nucleophile. Okay, so it is a second order reaction where rate is proportional to the substrate and the nucleophile. If you remove the proportionality sign here, you can replace it with the rate constant, which we'll write it as K. Okay, this you have studied in Chem 152, General Chemistry second semester, where how the rate of the reaction can be represented in terms of the concentration of the reactants. Where here, when I put square brackets here, which means the concentration of the substrate, which is my alkyl halide, and then here it is the concentration of the nucleophile. Okay, so here this particular reaction, which we refer to as SN2, where S stands for substitution, N stands for nucleophilic, and the 2 represents the second order kinetics. Okay, so we call this as a substitution nucleophilic bimolecular reaction. So it's a bimolecular reaction because the rate is depending upon the substrate, or two things here, substrate and the nucleophile. So we call this as a SN2 reaction. So what happens here is that the nucleophiles, it looks like this SN2 mechanism happens as a concerted mechanism. Concerted means all these, the attack of the nucleophile, the leaving group leaving happens at the same time, and this type of reactions are called as concerted reaction. So as shown in this figure, this is the mechanism where the it's actually everything happens in a single step. There are no intermediates, and also the key factor is that the OH minus of the nucleophile attacks from the opposite side of the leaving group. Okay, so it's not coming from the front side, but it's coming from a back side because the front is occupied by the leaving group. So these are some important features of this SN2 reaction. So the nucleophile attacks the carbon atom because that's my electrophilic carbon. Br is pulling the electron towards itself, as a result which carbon becomes my electrophilic carbon, and so the nucleophile attacks here, kicks out the bromine, so we get a transition state where bond formation and bond breaking is happening, and this is a transition state, and then quickly the Br minus is removed and you get the OH attached to the carbon atom. So since this attack happens from the back side, we get inversion of stereochemistry. See, we started with an S stereochemistry and we end up in an R stereochemistry. Okay, so you can look at this in a with an electrostatic potential map. So this is my nucleophile, okay, and this is my substrate, which is my alkyl halide, and you can see that here this is my nucleophile. Okay, so this is my nucleophile. So this is my leaving group. Okay, sorry, this is the leaving group, the one which we have marked it black here. That's my leaving group, which is the halogen. Okay, so we have a good leaving group halogen substrate. So the nucleophile does a backside attack on the carbon atom, kicking this one out. So we get a intermediate which looks like 5-member to the carbon atom, but it is these bonds, the dotted bonds shows that this bond is being made with the nucleophile and this bond is being broken from the with the leaving group. And finally, once the leaving group leaves, the nucleophile attaches itself to the carbon atom, and you can imagine like a umbrella turning back on a windy day. So it happens with the inversion of stereochemistry. So everything happens in a single step, right? So that explains why our reaction is of second order and second order kinetics, that in a single step, both alkyl halide and the nucleophile are important, right? So this is not happening in 2 steps, it's happening in one single step where the rate of the reaction depends upon both the concentration of the nucleophile and the concentration of the alkyl halide. Okay, so that's the SN2 reaction. This graph here tells us how the SN2 reaction occurs and what are the different variables that affect the reaction, so that sometimes we can get the SN2 reactions to be fast and some of them are slow. So, and how we can manipulate to get them to high yield reactions. So if you look at the activation energy in the diagram here, a change in the reaction conditions can affect the activation energy. Okay, so the red graph is showing that if you have a smaller activation energy, then you can get the reaction to go faster. And here with the black graph here, you have a larger activation energy which will make the reaction go slower. So any factor that will make this delta G smaller, that would help in increasing the rate of the SN2 reaction. Okay, so we are looking at the effect of changes in reactant and transition state on a reaction rate. So it's telling that the graph A, higher reactant level, corresponds to a faster reaction, and here the second is showing that if you have a transition state that is lower, then that also helps us to make the reaction faster because the delta G is smaller here. So the first factor we'll look into is what is called as the steric effect. Okay, so we are looking at ways by which we can make the SN2 reaction go fast or give us more yield. Okay, so it looks like that since the rate depends upon the substrate means the alkyl halide, so what kind of substrate you use is important. So we're looking at a picture where we have a primary alkyl. So this is actually a methyl alkyl halide. This is a primary alkyl halide. This is a secondary alkyl halide and a tertiary alkyl halide. So when we have different alkyl halides, it is seen that the reaction happens the fastest with methyl. So the reaction is fastest with methyl, and then it is primary, then it is secondary, and then it is tertiary. So it looks like bulkier the alkyl halide is, slower would be the reaction. And the reason is when the carbon atom is shielded by larger groups, then the attack of the nucleophile becomes difficult. So this arrow is showing the attack of the nucleophile. So in case of a methyl group, you can see that the nucleophile can attack this carbon atom here, right? This gray colored carbon atom much more easily than when it is in a primary, or primary is better than a secondary, and secondary is better than a tertiary, because here in tertiary you can see that the nucleophile can hardly see the carbon atom on which the attack should happen. So sterics plays a big role in looking at the rate of the reaction. So we prefer that SN2 reactions be conducted using a methyl or a primary. Secondary is okay, but tertiary are very, very slow. And vinylic and arylic, we looked at the structures of them. Vinylic and arylic do not show reaction towards SN2 displacement. Okay, this is because the incoming nucleophile will have to approach the plane of the carbon double bond, and that would be a difficult part. Okay, so for vinylic and arylic, the SN2 reaction does not happen, does not occur. If you remember what are vinylic, vinylic would be when the double bond is bearing the halogen, and then arylic is when the halogen is on the benzene ring, right? So this would be difficult for the nucleophile to approach, because we already now pi bonds are there, they're rich in electrons, so that would be a for the nucleophile to approach this plane of carbon-carbon double bond would be a difficult process. Okay? So these two do not react. Okay. Alright, so you have to remember that which would be the best substrate. Methyl and primary works the best. Secondary is okay, but tertiary is the worst one. This is the worst, and this is the best one. Alright, now the other factor, well, here it is showing this SN2 reactivity again. We're doing a comparison of tertiary versus methyl, and you can see that the tertiary is very less reactive as compared to the methyl alkyl halide. The next factor that affects the here is the vinylic and the arylic, which I was explaining. Nucleophiles also affect the rate of the reaction as in SN2. Why? Because again, recall, the rate of SN2 reaction is proportional to the alkyl halide and the nucleophile. They both are part of our rate determining step. So we already looked at the kind of alkyl halide that would work the best, that is primary or methyl, and then let's look at what kind of nucleophiles work the best. Okay? So we can use a wide variety of nucleophiles in this reaction. However, the best nucleophile that would work for an SN2 reactions are which we call it as strong nucleophiles. Okay? And strong nucleophiles are generally the ones that have a full negative charge. Okay? So when we talk about nucleophilicity, we also have to think about basicity. So when comparing So when you compare nucleophiles, some of the nucleophiles can also act as bases. For example, OH minus can be a nucleophile and a base, whereas some nucleophiles like cyanide, Cn minus, they are more nucleophilic than they are basic. So you should be able to compare nucleophilicity and basicity. The other factor is that if you go down the group on a periodic table, the nucleophilic character is greater than as we go down. Okay, so for example, an SH minus nucleophile would be stronger or more stronger than a OH minus, because sulfur lies below oxygen on the periodic table. Or you can compare the nucleophilicity of iodine. Iodine is a better nucleophile than a chloride, which is a better nucleophile than a chloride. Okay, so down the group, nucleophilicity increases. Okay, it increases. And also the other factor is that negatively charged nucleophiles are better. So for example, if you compare OH minus and water, they both are nucleophiles, but this would be a stronger nucleophile. So you need strong nucleophiles for SN2 reaction. That is what is preferred. In your textbook, when you read about it, you can some more examples of nucleophiles which are fully negatively charged, like Cn minus or CH3, O minus. Okay, these are examples of strong nucleophiles. There is another nucleophile which is ethoxide, okay, like CH3, CH2, O minus. Okay, it's ethoxide. This is methoxide. However, if you look at T-butoxide, okay, so again, if you look at T-butoxide, this is the structure of that, CH3 thrice C, and then we have it connected to O minus, okay, and generally it is has a potassium as its counter ion. So if you look at this, looks like a negatively charged species, so it should be a strong nucleophile. However, it is not a good nucleophile for SN2, again because it is bulky in nature. Okay, so we do not want bulky nucleophiles, we want small nucleophiles. So some of these are good ones. Okay. Now the next factor that affects the rate of the reaction is the leaving group. Okay, leaving group propensity. So that's another variable that can affect SN2 reaction. So greater the or easier the leaving the best leaving groups in SN2 reactions are the ones that can be stabilized once they leave. Okay, so for example, weak bases such as Cl minus, Br minus, and tosylate ions, they are good leaving groups, while strong bases like OH minus and NH2 minus, they are poor leaving groups. Okay, so so that's why if you take an alcohol, right, it's very difficult to do an SN2 reaction, substitution reaction, just by removing the OH, because this is a very poor leaving. Okay, on the other hand, if you have CH3Cl, then chloride is a good leaving group. So these are weaker bases. Okay, so when this is removed, you get chloride as the base, which is a weaker base, and they are stabilized much more than stronger bases like OH minus or NH2 minus. Okay. And tosylate is also a very good leaving group. Tosylate is actually one of the best leaving groups, and OH minus or NH2 minus or methoxides are poor leaving groups. Okay. Among halogens, now since this whole chapter is where we only deal with halogens as our leaving group, iodine would be the best leaving group, then comes Br, then comes chloride, and then fluoride. So larger the atom, larger the size of the atom, greater would be the tendency for it to leave. Okay, and so it is important to know that poor leaving groups which are good, and we indicate that F minus and OH minus and OR minus are not displaced by nucleophile. So these are poor leaving groups. Okay, an example here is shown with reaction of alcohol with sulfonyl chloride or PbR3. This is a reaction actually we looked in chapter 10. We see that here OH minus is a poor leaving group, right? OH is a poor leaving group, so our reaction with SOCl2 makes it into a good leaving group. Okay, so that's the whole idea. Same thing with PBr3. It makes it into a good leaving group, and that's how the product is formed. All right, or you can make the alcohol into a tosylate. Okay, like in this case, you can change it into a tosylate, and then it becomes a very good leaving group. Okay. All right, and finally, the factor that the variable that strongly affects SN2 reactions are solvents. So, what kind of solvents are good for SN2 reactions? We call these solvents as polar protic solvents. So, you want polar protic solvents favor the reactions, and polar protic means solvents which are polar in nature but do not contain OH or NH group. Okay. So water will not be a good solvent because it contains OH bonds, or ammonia will not be a good solvent because it contains NH2. On the other hand, acetone, right? So this is acetone. It is a polar compound and it does not have OH or NH groups in it, so it will be a good solvent. So the reason why we do not want polar aprotic solvent. Okay, sorry, I've made a mistake. So we have polar aprotic solvents that are good for our reaction in SN2. So protic solvents such as methanol or water or ammonia, they slow down the reaction. Why? Because the nucleophile will get solvated. Solvated means it will be surrounded by the solvent molecules due to hydrogen bonding, and therefore we do not want polar protic solvents, but we want what is called as polar aprotic solvents like DMP, HMPA. Okay, that's it's a common solvent that is used, hexamethyl phosphoramide, and we can use dimethyl sulfoxide, which is abbreviated as DMSO, or acetone is a good solvent, or acetonitrile is a good solvent. So solvent is also an important factor. So summarizing, these are all the factors which affect the SN2 reaction. So we want an unhindered substrate. We want a good nucleophile. You can look at the energy diagram of how an unhindered substrate has forms the product easier, and then a good nucleophile. You can see that that has a lower delta G. Then good leaving group again has a smaller transition state, and then polar aprotic solvent has a smaller delta G. Okay, or the transitions. The energy of activation. Okay, so that's what we are looking at, how the energy diagrams shows the effect of a substrate, a nucleophile, leaving group, and solvent on an SN2 reaction. So we'll talk about SN1 reaction in the next video.